Welcome to the Deep Dive, where we unpack the latest in AI research to keep you right at the cutting edge.
Hey, everyone.
Today, we're diving into a paper that's really caught our eye, especially if you're into passive sensing or generative models. It's called High-Resolution Efficient Image Generation from Wi-Fi CSI using a pre-trained latent diffusion model.
Yeah, this one introduces something called Latent CSI. And look, for our audience, ML engineers, researchers, this is a really significant shift in architecture, I think.
Definitely.
We're basically watching a very specialized sensing task get plugged into the power of these huge foundational models. It's pretty cool.
It really is.
Thanks.
Okay, so if you just need the quick version, the elevator pitch, here's the 1-minute rundown on what Latent CSI actually does.
Right, so the big idea. What they're doing is taking standard Wi-Fi signals, the channel state information, CSI, and using it to reconstruct surprisingly high-resolution RGB images of what's happening in a room, particularly like human shapes and poses.
And the innovation here is pretty clever. Instead of building some giant generative model from the ground up, which is, the usual slog,
Yeah, painful.
they take a pre-trained latent diffusion model, think stable diffusion, and they just swap out the part that normally looks at images. They replace it with this custom, much lighter CSI encoder.
So it learns to translate the radio waves directly into the language that stable diffusion already understands. Really neat.
Impact and efficiency? Well, this thing is fast. Training times are up to 3 times quicker compared to older methods that work directly in pixel space.
And crucially, the quality, the perceptual quality is way better. They measure this using FID, fresh inception distance, and the scores are much lower, which is what you want.
Lower is better for FID, yeah. And the killer feature, maybe. Because it's built on top of an LDM, these images it generates, they're naturally text controllable.
Right, you can feed it a text prompt to tweak the output, change the style, add details, things you just couldn't do before with CSI sensing like this.
So that's the core. Faster training, better looking images, and you can control it with text. Okay, let's dig in properly. Why CSI for images, and what were the old methods missing?
Well, the appeal of CSI is, honestly, it's everywhere. Wi-Fi is ubiquitous, right? And this CSI data, it's basically a detailed fingerprint of how radio waves bounce around a room.
It's calculated anyway for the Wi-Fi to work properly for signal equalization.
Exactly. It's already there. And it's packed with information about the environment, obstacles, movement. So people have used it for years for simpler tasks like figuring out if someone's sitting or standing, basic pose estimation, activity classification, even like breathing detection.
Okay, but those are relatively low-dimensional outputs, right? Predicting a class label or maybe a few joint coordinates, generating a full high-res image, say 512 by 512, that's a whole different beast. It's high-dimensional reconstruction.
Totally at scale. And that's where the previous approaches, mostly using generative adversarial networks or GANs, kind of hit a wall.
Jans, always an adventure.
Hey, yeah. Some early work showed promise, generating maybe 64 by 64 pixel images from CSI. So proof of concept, yes. But trying to push GANs to high resolutions, it gets incredibly complex.
You're training 2 networks that are essentially fighting each other. Getting them stable is hard, convergence is tricky.
It's a nightmare. You often get mode collapse, where the generator just spits out the same few images. Plus, the computational cost is huge, and they need really careful, finicky tuning.
So if you're aiming for efficiency, which this Latent CSI paper clearly is, GANs are almost the opposite of what you choose. You've got double the model complexity right off the bat.
Precisely. And, there were other attempts maybe using VAEs, variational autoencoders, but they typically struggled with generating sharp details. The images often looked kind of blurry or washed out.
So the field was sort of stuck, either stable but blurry, or potentially sharp but unstable and computationally expensive.
That's a good summary. And this brings up a really important point that Latent CSI tackles directly.
Right, because if you train a model end-to-end, just mapping radio waves straight to pixels, it can sometimes learn too much. It might start reconstructing fine visual details unintentionally, maybe even things like facial features, because it's overfitting on the ground truth images used during training.
That's a genuine concern. If the model gets too good at pixel-perfect reconstruction, it might leak sensitive visual information. Latent CSI builds in a defense against this.
How so?
By design, it forces the information through this low-dimensional bottleneck, the latent space of the diffusion model. High-frequency details, the kind that define specific faces or textures, they just don't make it through that compression process easily.
Ah, okay. So it's like an intentional information bottleneck. It preserves the main structure, the pose, the location of the person, but filters out the really fine-grained, potentially identifying details.
Exactly. It's engineered data loss, in a sense. You get good visual quality for the task, like tracking a person, but you bake in a level of privacy protection against exact visual duplication. It's a smart trade-off.
A kind of built-in anonymization through the architecture itself. Very interesting. Okay, let's get into the architecture then. How does Latent CSI actually use Stable Diffusion without, retraining that massive model?
The magic word is transfer learning. They take Stable Diffusion v1.5, which is publicly available and already trained on, like billions of images.
A monster model.
A total monster, yeah.
Okay.
And they basically just attach a new front end to it. They keep the powerful image generation part, the UNet denoiser and the VAE decoder completely frozen. No retraining needed there.
So the heavy lifting for actually making the image is done by the pre-trained Stable Diffusion.
Right. All the new training focuses on that custom front-end piece, the CSI encoder.
Now, about the setup. The paper mentions needing an RGB camera, but only during training, right?
Crucially, yes. You need the camera during the training or calibration phase to get the ground truth images that correspond to the CSI measurements you're collecting. But once the CSI encoder is trained for actual inference, you only need the Wi-Fi signal.
So you could deploy this in places where cameras aren't allowed or practical due to privacy or just logistics.
That's the idea. The whole system relies on the assumption that there's enough shared information between the radio signal patterns and the visual scene for the encoder to learn that mapping robustly.
Okay, let's trace the data flow. In a standard image-to-image diffusion pipeline, you'd feed an image into a VAE encoder, get a latent representation, the UNet refines it based on noise and maybe text prompts, and the VAE decoder turns it back into pixels.
Correct.
Latent CSI basically cuts off that first step, the VAE encoder that looks at pixels.
Throws it out entirely.
And slots in their own CSI encoder instead.
Exactly. And the whole job of this new CSI encoder is to take the raw CSI measurements and transform them into a latent vector that looks exactly like the kind of latent vector the original VAE encoder would have produced for the corresponding ground truth image.
So it has to learn the language or the structure of Stable Diffusion's latent space, but starting from radio waves instead of pixels.
That's the core task. And importantly, as you said, the big components downstream, the UNet, the VAE decoder, their weights are frozen. Not touched at all during this training.
Doesn't that limit things? I mean, Stable Diffusion was trained on a massive, diverse data set of natural images. Now you're feeding it latent codes derived from CSI data of people in, like, a lab environment. Isn't there a mismatch? Won't the frozen LDM struggle or introduce biases?
That's a really sharp question. And yes, there is an inherent limitation there. The system's output capabilities are constrained by what the original Stable Diffusion learned. However, the trade-off is enormous efficiency. If they tried to fine-tune the UNet, forget it. You're back to training a massive model, huge compute costs, long training times. By keeping it frozen, they leverage its incredible power to synthesize plausible images from any well-formed latent code. The bet is that the LDM is robust enough.
So the challenge shifts entirely to training just that relatively small CSI encoder to produce the right kind of latent code to feed the beast.
Precisely. And that training happens in the lower dimensional latent space, which is computationally much, much cheaper than trying to predict pixels directly.
They're basically teaching the CSI encoder to mimic the output of the original VAE encoder, specifically the latent mean vector.
That's the technical goal, yeah.
Yeah.
Minimizing the squared error between the CSI encoder's output and the target latent mean from the pre-trained VAE.
And what about the CSI input itself? Are they using everything amplitude and phase? Phase can be tricky with Wi-Fi.
Good point. No, they made a practical choice here. They only used the CSI amplitude information. They calculated simply from the real and imaginary parts.
Ah, smart. That avoids all the headaches of phase unwrapping and synchronization issues you get in real-world Wi-Fi setups. Makes the input much more stable.
Definitely simplifies things and likely makes it more robust.
Yeah.
And the architecture of this CSI encoder, they didn't go for something totally alien. It actually mirrors the structure of the LDM's VAE encoder quite closely. Starts with a fully connected layer, then has these upsampling blocks, the 4 of them, that increase resolution while decreasing channel depth. And they include cross-attention layers too, similar to the VAE.
Okay, so it's designed to fit structurally into that LDM pipeline. It's like a custom-built adapter plug, specifically shaped to connect CSI data to the LDM's input socket.
That's a perfect analogy. An adapter plug trained to translate radio signals into latent thoughts.
So the million-dollar question, does this clever adapter actually work well in practice? Let's talk evaluation.
Right. And testing, this isn't just about checking pixel by pixel accuracy, because that's not really the main goal.
They want perceptual quality, right? Does it look like a person in a room?
Exactly. So to isolate the CSI encoder's performance, they ran tests with the diffusion part, essentially turned off, setting the noising strength to 0. This shows what the encoder predicts directly before the LDM synthesis kicks in.
And the metrics?
They use standard pixel metrics like root mean squared error, RMSE, and structural similarity index, SSIM, mainly for comparison with older methods, but the key metric was FID Frechet inception distance,
which is known to correlate much better with human perception of image quality than raw pixel differences.
Definitely. So dataset 1, this was their own data collection using wideband Wi-Fi, getting high-res 512 by 512 images, and crucially, it was in a realistic setting, not perfectly clean. There were occlusions, clutter, like a real room.
The messy real-world test, what happened?
The results were pretty stark. LatentCSI got an FID score of around 134. The baseline model, which tried to predict pixels directly using a similar encoder architecture, but outputting pixels.
The apples-to-apples comparison, just working in pixel space instead of latent space.
Right. That baseline scored about 268 on FID. Remember, lower is better.
Wow, okay. A jump from 268 down to 134 FID is huge. What does that difference actually look like?
It's significant. The higher score, 268, suggests the baseline's images likely had noticeable artifacts, maybe blurriness or distorted human shapes, things that just look wrong to us. The 134 score for Latent CSI implies much more coherent, plausible images. The person looks like a person, the pose makes sense. The LDM's generative prior helps smooth over the imperfections from the raw CSI prediction.
Filling in the gaps, plausibly.
Exactly. And the efficiency numbers back this up too. Training the pixel space baseline took about 36 seconds per epoch on their hardware. Latent CSI, just under 12 seconds per epoch.
So roughly 3 times faster to train.
Yeah, a 3x speed up. That's not trivial. For anyone doing ML research or engineering, that speed up means faster iteration, bigger experiments, maybe deployment on less powerful hardware. It makes these kinds of high-res sensing projects much more feasible.
Okay, now what about dataset 2? This used a public dataset subset, MMFi, lower spectral resolution Wi-Fi, but the environment was cleaner, less background variation.
Right, and here, things got a bit more nuanced. On the simple pixel metrics, RMSE and SM, the baseline model actually did slightly better.
Huh. Why would that be?
The likely reason is memorization. Because the background was so simple and static in that dataset, the pixel prediction baseline could probably just learn to reproduce those background pixels really well, boosting its score on those simple metrics.
Ah, so it was good at painting the unchanging parts of the scene accurately, pixel by pixel.
Plausibly, yes.
Huh.
But, and this is the key point, even though baseline 1 on R and SM, Latent CSI still crushed it on the perceptual metric, FID.
What were the FID scores there?
Latent CSI got around 28, while the baseline was up at about 47. Again, lower is much better.
So even when the baseline was better at raw pixel matching for the static background, Latent CSI produced images that looked more realistically like a person?
Precisely. Especially when they focused the FID evaluation just on the area where the human subject was. It shows that Latent CSI is better at the actual task, reconstructing the subject plausibly, avoiding weird artifacts, even if it doesn't perfectly nail every background pixel. It really highlights why perceptual metrics like FID are crucial for generative tasks.
Makes total sense. You care if the person looks right, not if the wall texture is perfectly reproduced. And then there's the final piece, the text control. This seems like a bonus feature almost, but a powerful one.
It's a direct consequence of using the LDM's latent space. Because that space is inherently conditioned on text prompts in models like Stable Diffusion, they get that capability essentially for free.
So you can take the initial image generated purely from the CSI.
It gives you the basic pose and location.
And then you can add a text prompt to refine it or change its style completely.
Yeah, the paper shows examples like taking the initial output, which might look like a basic photo, and applying a prompt like a drawing of a man in a laboratory anime style. And it works.
That's amazing. You're steering the output creatively using language based on an initial guess derived from invisible radio waves. It connects physical sensing directly to generative AI tools.
And it connects back to the privacy aspect too, in an interesting way.
How so?
Remember, the bottleneck prevents reconstructing fine details from the CSI. The text prompt lets you add plausible details back in, but based on your explicit instruction, not based on leaking sensitive data from the original signal.
Ah, I see. So if the raw CSI just shows a person standing there, you can add a prompt like wearing a red shirt, and the LDM will synthesize that detail, making the image more useful or specific, without implying the system actually saw a red shirt in the radio waves.
Exactly. It balances the privacy limitation with user control and visual plausibility. It's synthesis guided by the CSI structure and the text prompt, not direct reconstruction of potentially private visual data.
Okay, wrapping up then. The main takeaway seems to be that Latent CSI offers a really compelling path forward for CSI-based imaging. It cleverly sidesteps the complexity of training GANs or huge pixel space models by hijacking a pre-trained LDM.
Right. It trades off maybe some pixel-perfect accuracy, especially on simple backgrounds, for huge gains in training speed, much better perceptual quality where it matters on the subject, and this unique text control capability.
It's a smart use of existing powerful tools.
Fundamentally, yeah. It shifts the paradigm. And looking ahead, this really opens up questions. We're seeing foundational models touch everything. So the provocative thought for you, the listener, might be, what comes next?
Where could this go?
Well, if this approach works well for 2D images by optimizing just that front-end CSI encoder, could we adapt this for different LDM architectures? Maybe models trained specifically for, say, 3D scene understanding or volumetric reconstruction. Could we design specialized CSI encoders to talk to those latent spaces, moving beyond just 2D images from Wi-Fi signals?
Real-time 3D reconstruction of a room using just Wi-Fi and a clever encoder feeding a 3D-aware diffusion model. That would be something else entirely.
It feels like the direction things could head, leveraging these massive pre-trained models for increasingly sophisticated sensing tasks. Definitely something to think about.